Today's topic is ceramic based gas sensors. Obviously, it is a very interesting application of ceramic materials, where ceramics, particularly oxides, can be used for the purpose of sensing the presence, not only the presence or the even measuring the concentration of some of the specific gases at very low concentrations, mostly less than 1% or even in the ppm range. We will start with a definition, simple definition. Of course, I am sure it is quite known to everybody. The gas sensor, what is a gas sensor? Gas sensor is nothing but a device that produces a measurable response. Normally, it is an electronic signal to a change in concentration of gaseous species. It may be categorized as a chemical sensor. In fact, sensors can be, there will be two major groups of sensors. There are many different parameters one can sense with various types of sensors. One is basically a physical sensor, another is a chemical sensor. Since we are talking about a chemical species, in this case it can be categorized as a chemical sensor. What are the different properties on which sensors are based? Different properties of ceramic materials may be utilized in different ways to sense the presence or to measure the concentration of gases. In general, we are talking about electronic signal. So, the most convenient way is to utilize or exploit the electrical conductivity of the oxides. As we know, there are many different kind of wide spectrum of properties available with the ceramic materials. Some of them semiconducting, some of them metallic conductivity. There are ionic conductivity, dielectric property, and even piezoelectric property. All these properties can be exploited because there is a connection or there is a connectivity with the electrical properties. Basically, there are many different kind of electrical properties can be utilized to sense the presence of some gases, specific gases. In case of the last one, of course, we will not be discussing much about here, because we have mentioned briefly that piezoelectric property of the ceramic materials can be utilized to fabricate a SAW device, and that SAW device in the presence of some of the gases, particularly moisture, the characteristics of this SAW device changes, and by monitoring the change one can find out what is the concentration of this moisture in presence of the SAW device. Well, if we look at the structure of ceramic materials in general, we have three situations. In the left, we have a porous structure. Basically, ceramics are porous and they are polycrystalline materials, and they have a porous structure. So, you can have pores in between the material, in between the sample. Okay. So, you have not only the air outside, but also inside, present inside the material, inside the structure. So, that is because of the pore structure. So, you have presence of Knudsen diffusion. Through a Knudsen diffusion, assuming that pores are continuous, and open pores, what we call the open pores in ceramic terminology. That means, there is a connectivity from the internal pore to the outside ambience. So, these are so the gas can go in through the pores and comes in contact with the surface of these individual crystals or individual grains. Okay. So, this is one kind of structure. In fact, this is a very common structure in ceramics. Whenever you try to make a bulk ceramics, a thicker ceramics, or even thin ceramics like thick films, okay, relatively thick, relatively thin, maybe several microns in thickness. So, but even then you have porous structures. So, this is one kind of situation. This is of course a substrate on which these materials can be deposited with a porosity, some amount of porosity. There are other two situations here. These are basically related to thin films. One can make thin films, very dense thin films. There also thin films can be porous, but normally thin films are not porous, but they may have polycrystallinity in it. So, they may not be single crystal or but we have polycrystalline materials, and in between we have grains, in between you have grain boundaries. So, these are the two grains and in between there is a grain boundary, and grain boundaries are normally a defective structure, and the diffusion even for the gases can take place much faster. So, the activation energy for diffusion of the gaseous molecules or atomic gases, atoms are much faster along the grain boundaries than through the bulk. Okay. So, it is actually here also the gases can come into the material, not through the pores like this. These are more molecular diffusion, but here it can be a atomic diffusion and in the form of some ions even. So, gases can come in either through the grain boundaries, primarily through the grain boundaries. So, the surface, this is one kind of surface, this is one kind of surface where the surface is exposed to the atmospheric gas. But here this is also another surface inside, internal to the material, and this is also a discontinuity, crystallographic discontinuity, and gas can diffuse in. So, it can, here there are two different surfaces, one is the outside external surface and the other is this called internal surface. In both these cases one can have roll up surface where so far as the conductivity is concerned or the conduction mechanism is concerned. Now, how these surfaces of, particularly we are talking to start with, we are talking of semiconducting property of the oxides and semiconducting oxides. So, how these surfaces can be different from the bulk of the material. In a semiconducting material, the electron transfer is relatively easy compared to the insulating materials. So, you have large number of electrons or holes available in the structure, and all these materials have a inherent property to adsorb some of the ionic species, particularly oxygen. And as you can see here, these are two different grains of a ceramic material. Basically, it is a semiconducting material. So, these are actually the conduction electrons, which has been just denoted here. That means, initially these are a semiconducting material. So, fairly large number of conduction electrons are already available because of the defect structure, because of the non-stoichiometry, and of course, because of the ambient condition and so on. So, a semiconducting oxide, there may be electrons if it is a n type semiconductor, if it is a hole conductor or a p type semiconductor, there will be holes. Now, if you have a enough of electrons, electron will have certain energy levels, and that can be represented in the form of a band diagram. This is the so called conduction band of the electrons present here, okay. And these are the donor levels close to the conduction band. So, you have in the conduction band, you have already some electrons available which are free to move under the application of the electric field. So, these are the electrons already available. However, when there is a adsorption of certain species, gaseous species in particular, here it has been shown that surrounding this grain, you have a layer of adsorbed oxygen ion, O minus. It is not O2 minus, it is actually O minus. So, oxygen atom has taken up an electron from this solid, and so is become O minus. So, it has been, the electrons have been taken up from the outer surface. So, there is a creation of what we call the depletion zone or depletion region, that means electrons are no longer there. Okay. So, electrons which was inside the crystal is still remaining, but because of the electrons have been picked up by the oxygen which is available in the atmosphere. So, that has O minus, and that electron is now attached, it is localized with the oxygen atoms, and therefore, it is no longer free. It is no longer free. So, there is an insulating layer. These green layers actually are the insulating layers, where the number of electrons, free electrons, is very less, whereas inside you have a conducting grain. So, because of the presence of sufficient amount of oxygen most of the time, because basically it is an oxide and it is placed in an oxide environment or air environment. So, you have oxygen, sufficient oxygen atoms, and they get adsorbed on the surface, and during this adsorption process they pick up, each one of the oxygen atom picks up one electron from the surface layer, and as a result the electron density here is depleted and you get a insulating layer. You get an insulating layer surrounding all the grains. So, if it is a whether it is a porous material or a non-porous material does not matter, because there are still surfaces available. Okay. The surfaces available, whether it is a free surface or a discontinuity in the crystallographic orientation. So, that is like grain boundaries, both acts as more or less the same manner, and you get electron depletion zone surrounding the crystals, surrounding the grain boundaries, whether it is porous or non-porous, it does not matter. Right. Now, as a result of that, a insulating barrier is created, and the band, the conduction band bends here, because you have an insulation barrier. So, the electron cannot move so easily from this point to that point. Okay. It has to cross a particular energy barrier. This, because of the depletion zone, the band has bent here, and you have a larger energy. So, that electron, if it go to from this side or this side to that side, then it has to go through a larger energy barrier, and that can be calculated, and it has been expressed at QVS, charge into some amount of this height. Okay. So, this height is actually this expression. So, the primary reason of the depletion zone is the adsorption, that which is the inherent characteristics of all semiconducting oxides in presence of enough of oxygen. So, this is the characteristics, and a depletion zone and adsorbed oxygen ions, the conduction electron, these are conduction electrons here as well as in the band here, and these are oxygen negative sign, one negative sign. So, O minus, and that comes in, that forms automatically layer on its own. It does not need any external influence to create that. Now, with this one can have, so we have created or there is a presence of some surface layer, basically an insulating layer or an adsorbed layer, and that layer can be a continuous one like this. Okay. So, the electron can move through this continuous phase, which is a slightly insulating phase compared to the conduction phase, conducting phase, which is the bulk of the grains. So, it can be a continuous phase if there is no boundary, or even if the boundary there may be another discontinuity here, but it may be a continuous phase. Otherwise, if the pores are there, then it can be a discontinuous phase. Okay. So, it does not matter whether it is continuous or discontinuous, there is a difference, in conductivity or the nature of conduction between this layer and the bulk of the material. Okay. So, here this kind of barrier has been created because it has been a discontinuous layer. Now, the expression for conductivity for the bulk and the surface conductivity or the barrier layer is different. Okay. This is a very common expression. We have seen earlier that for any oxide the defect concentration, the non-stoichiometry changes with the kind of environment it is exposed to, because there is a oxygen in the oxide, in any oxide, and oxygen is also available in the environment. So, there is exchange, there is an equilibrium of the oxygen concentration or oxygen partial pressure, or in other words oxygen potential between these two solid and the gas. So, there is a solid gas exchange, and you will always get a PO2 dependence, of the conductivity. So, the conductivity, particularly when they are non-stoichiometric oxides, you will get a PO2 dependence. That means the conductivity is not only dependent on the temperature in this by this Arrhenius kind of equation, but in addition you have PO2 to the power plus minus 1 by n. So, both PO2 and temperature controls the conductivity, particularly the bulk conductivity, and there is a equilibrium between the oxygen potential or oxygen concentration on the in the environment and the oxide. So, there are plus minus, because depending on the situation it may be either plus 1 by n or minus 1 by n, and if one remembers that it depends on what kind of defect concentration, what kind of non-stoichiometry the material has. If it is an oxygen deficient oxide, then it is a n type semiconductor, and the conductivity increases with decreasing PO2. So, the minus sign applies. So, minus sign applies for a oxygen deficient oxide, whereas plus sign applies with oxygen excess oxide or metal deficient oxide. So, depending on the nature, and as we have earlier discussed that this is an inherent property of the semiconducting oxide, either it may be oxygen deficient or a oxygen excess oxide. So, depending on that, either the minus sign or the plus sign will be applicable. So, but the most important aspect to note here is that any oxide, for any oxide there is a partial pressure dependence. So, partial pressure is controlled by the environment. So, the oxygen potential is also controlled by the presence of other gases in addition to the oxygen. Well, in air you have only oxygen and nitrogen. So, no other gases influence the PO2, but if there is some hydrogen, if there is some reducing gases, the PO2 will change the partial pressure surrounding the atmosphere, and therefore, that has a bearing on the bulk conductivity of the oxide. So, there is a direct relationship between the oxygen concentration or oxygen potential of the surrounding atmosphere to the conductivity of the oxide. Okay. So, that itself says that the conductivity will vary with the concentration of the gases, and one can monitor the gas concentration just by measuring the conductivity. So, that is very basic principle, but so that is so far as the bulk conductivity is concerned, when we are not considering the adsorbed layer or the surface layer. If we are talking about the surface layer, then there is a band bending, as we have seen, and some surface states are created in the energy band diagram, and as a result there is a enhanced barrier height. So, the barrier height, there is a creation of a barrier height at the junction, and so the surface conductivity is also exponentially dependent on the surface, on the barrier what is created, energy barrier that is created. This is more or less the same expression, except that there is no PO2 term. Okay. So, this is not dependent on the environment, it is basically dependent on, as we have seen earlier, it is on this adsorbed layer. Okay. Once the adsorbed layer is formed, then it is immaterial what kind of environment it has, particularly in terms of PO2, but it will certainly change, it will certainly change if the environment change, but we do not have that kind of a direct relationship like in case of a bulk conductivity. The relationship is slightly different. So, this is the conductivity of the surface, and that is the conductivity of the bulk material. Incidentally, the conductivity, this conductivity is relatively high, magnitude of this conductivity on the same material, the magnitude of this conductivity is relatively high compared to this value. So, whenever the adsorbed species on the surface, it is the surface which predominates so far as the conduction process is concerned. What are the possible sensing mechanism then? We have seen there is a oxygen adsorption on the surface of the semiconducting oxides, and this is what happens. Oxygen from the environment comes in as a contact as a molecule, and then on the surface it is actually atomized, gets instead of molecules it gets to atoms. So, it is by through a catalytic process. So, all oxide surfaces have some catalytic activity, and that catalytic activity leads you to the presence of oxygen atoms. Okay. Now, these oxygen atoms, as mentioned earlier, that it takes up electron from the bulk of the material, primarily from the close to the surface. So, it picks up electron and then becomes a monovalent or negatively charged oxygen atom or oxygen ion, and that gets adsorbed on the surface, because there electrons, there is a transfer of electrons from the solid, and it picks up electron from the solid and gets adsorbed to the. So, it is getting localized at the surface. So, you have a layer, you have layer of oxygen adsorbed layer on the surface. Now, this oxygen layer, when exposed to a residual reducing gas in particular, the interaction with surface chemisorbed is a chemisorbed oxygen layer, oxygen ion, in different ways. Let us say we have a gas like carbon monoxide, which is a reducing gas, it is in the environment, and then when it comes in contact with the surface where already adsorbed oxygens are there, it will react with that, and then it will convert to CO2, the oxidized gas, and in the process it will release this electron. In this process it will release this electron where it was taken from. Okay. So, in the presence of oxygen, the electron gets picked up from the surface. However, if there is a reducing gas, then oxygen, what was absorbed on the surface, it actually reacts with the carbon monoxide and oxidizes it to CO2, and the electron which was picked up from the solid is given back to the solid, particularly on the surface. That is what it has been shown in the pictorially. Here again you can see, if carbon monoxide comes from outside and then reacts with this adsorbed oxygen ion, it becomes CO2, and in the process this electron gets injected into the system where it was picked up. So, as a result, what would happen? What would happen? When carbon monoxide is not there, it was basically an insulating layer, and then in the presence of carbon monoxide, this becomes again a conducting layer or relatively conducting layer compared to the insulated layer which was created. So, that is basically the simple mechanism by which the electrical conductivity of the oxide as a whole will increase, because it is injecting electrons. Similar thing happens if there is some alcohols, and these are the kind of adsorbed oxygen ions. It reacts with oxygen and then it produces some adsorbed oxygen ions, and it changes to CO2, H2O, once again an additional electron is generated. So, by these chemical processes, whether it is a carbon monoxide or an alcohol like this, you can inject electrons, you can free electrons from the adsorbed sites or the adsorbed layers. Okay. So, this becomes free electron and it becomes conductivity increases. So, that is the kind of very simple mechanism, and adsorption has a very important role in the whole process. Well, it is not only the reducing gases, the oxygen or the conductivity can change, conductivity certainly can change. It is what we need, only a change. It is not necessarily one has to increase, but one can decrease also. So, change in conductivity, change in electrical signal. So, that is what a change in current, which is the measure, which can be measured, or which is a measure of the resistance of the material. In case of oxidizing gases like NO2, it can either be adsorbed on the oxide surface or can react with the pre-adsorbed oxygen ion as follows. Okay. So, NO2, for example, in case of in place of CO, if you have nitric oxide, then it can pick up electron, and instead of oxygen O minus, this species can also get adsorbed. Okay. This species can also get adsorbed on the surface, and then this also can react with the oxygen ion, okay, and by taking up 2 electrons. So, it will pick up 2 electrons and then this will be adsorbed and it will create another adsorbed ion. So, you can see, compared to the earlier one, here electron is not generated, electron is not actually injected in the system, but more electrons are being taken up, from the system. So, the conductivity in this case we will reduce. Well, anywhere, whenever, particularly when there is a n type conductivity in oxide, you will get that the reducing gases will enhance the conductivity, whereas oxides or oxidizing gases will reduce the conductivity. So, that way experimentally it has been observed that presence of either O minus or O2 minus species on the surface of oxides, like particularly like SNO2, the tin dioxide at above 2000 degrees centigrade. So, the presence of these kind of species has actually been detected on the surface of semiconducting oxides like SNO2. SNO2 incidentally is a very common oxide, which is an n type oxide, and it is a oxygen deficient oxide, SNO2 minus X actually. So, there is a non-stoichiometry there, and it has a n type conductivity. So, this is a very important oxide which has been historically used as a gas sensing oxide. Okay. And particularly it has been, these are conjecture, to a large extent these are conjectures, and it has been shown that these are the species really gets absorbed on the surface of SNO2, particularly at greater than 200 degrees centigrade. So, we will come to that, what is the temperature effect there. Temperature of course has an important role, not only the gas concentration or the type of gaseous species, but the temperature also has a very important role so far as the adsorption characteristics is concerned, and this adsorption characteristics is important for the detection of the gases, whether it is oxidizing gas or reducing gas. Incidentally, the oxidizing gas, it is less sensitive, whereas reducing gas is much more sensitive. Okay. So, it can consume the electrons or this oxygen, adsorbed oxygen species, and inject electrons. So, the reduction of resistance or enhancement in conductivity is much more significant when you have a reducing gas, or on the other hand when you have an oxidizing gas like this, the changes of conductivity are relatively small. Well, since adsorption is one of the major species, a major phenomena on the surface which gives rise to this kind of changes in conductivity, there is a very important role of catalysis, because initially we have seen that first of all oxygen molecule has to get atomized by a catalytic process, and then that oxygen atom picks up an electron. So, catalysis has also a very important role in determining the conductivity and also in presence of the adsorption in presence of some of the gases. In that context, palladium has a very important role in gas sensing. So, all the surfaces of the oxides are basically loaded with some amount of palladium. Palladium, as you know, it is a it can adsorb hydrogen, and it can also atomize hydrogen quite effectively. This kind of situation happens. Being a good catalyst itself, it helps in atomization of the gas molecules, not only hydrogen, but maybe hydrocarbons, and there are many other gaseous species which can be dissociated in presence of palladium as a catalyst at a relatively high temperature. So, palladium has a very important role, since we are depending, the total process is depending on the catalytic activity of that surface and the adsorption property of the surface of the oxide. So, if you can if one can load the surface with some very fine particles or fine islands of palladium, metallic palladium, that helps in the catalysis and adsorption, and in the process enhances the change in conductivity in presence of different gases. So, this is what happens. It atomization reaction takes place, and then atomized hydrogen reacts with the adsorbed oxygen ion and produces H2O and electron. Once again, the electron is liberated from this adsorbed surface, and therefore, the overall conductivity increases, because this electron is a bound electron. This electron is very much there, but it is locally bound with the oxygen atom. So, it is not available for conduction, whereas this electron is a free electron. Once it is freed from the oxygen site, it becomes free electron. So, by applying electric field, it can move, and therefore, one can enhance the conductivity. So, palladium has a very important role to play. So, whenever we talk about semiconducting oxides used for gas sensing, most of the time we use a palladium dispersion on the surface of the oxide. Next comes what is the basic design, how you can, whatever you have discussed so far is the basic principle on which a oxide can be used as a gas sensor or for sensing or measurement of gas concentration in presence of this oxide. Here how actual sensor looks like, or how it is designed. Of course, this design is a fairly relatively old design, although it is a standard design, but it is an old design. We will come to that, why it is old and what are the new designs one can have. To start with, we have a small hollow tube. Okay. It is alumina tube, a very small tube of the total diameter may be not more than 2 to 3 millimeter in diameter, and then on the surface you coat, one coats the oxide. It may be tin dioxide, zinc oxide, maybe other semiconducting oxides one can certainly use, but these are the two most common oxides used for this purpose, and incidentally both of them are N type semiconductors. In SnO2 it is oxygen deficient, whereas this one is also oxygen deficient, but it has the defect is metal interstitial. Here is an oxygen vacancy, then predominant defect, here it is metal interstitial, that is zinc goes to the interstitial side. So, this is an example of both of them are oxygen deficient, but the defects are different, point defects are different. One is a oxygen deficiency, oxygen vacancy, and another is zinc interstitial. Okay. So, these fine powders of either SnO2 or ZnO2 is actually coated, it is coated on the surface of the alumina tube. So, this is the actually active oxide. It is coated normally by different kinds, some kind of a binder, just like one makes thick films with the use of some organic vehicles. So, one can make a paste with some organic vehicles and then coat it, either brass it or screen print it on the surface. So, the overall thickness may be about 25 to 50 microns, okay. And of course, it is porous, and porosity is important. Porosity is important, as you have seen earlier, because the gas has to come in contact with the surfaces of the particles. So, controlled amount of porosity is important for this layer. So, there is a porous layer of the active oxide, and then of course, we have some electrodes. These are the electrodes to measure the changes in conductivity or resistivity. So, normally one can use the platinum leads, one can use, but for stability one can use gold layers or gold plated, okay. Otherwise, because they are noble metals, so they do not change even in the presence of oxygen or different gases. Otherwise, all other metals can either oxidize or make some compounds with these gases which has to be measured. Another important aspect of this is it is not a room temperature sensing. At room temperature, the resistivity of the material is very high, although we are talking about semiconductivity, but the resistivity may go up the order of mega ohm, centimeter and so on. Therefore, it cannot sense at room temperature, or the measurement becomes difficult, the impedance electrical impedance become difficult. So, it becomes difficult to measure the resistivity or the current becomes so low that one cannot measure. Therefore, it needs a heater. So, this is the hollow part of the ceramic tube is actually used to house a small coil, nickel chromium or nichrome coil, which actually heats up, and the temperature of operation is normally above 150 and it can go up to 300 degrees. So, you have to have a heater. So, there is a source, there has to be a current source to heat this, and then at that temperature, in presence of gaseous species, the conductivity or the resistivity will change, and you have to monitor that. So, this is very simple mechanism or simple design by which a gas sensor can be made. In fact, they have been made in huge numbers, and they are being have already been commercialized. So, they are commercially available gas sensors, and primarily developed in Japan, and then of course, the other countries also can make it now, and there are many modified versions of this kind of sensors. The overall dimension, as you can see, as I mentioned, is only about 2 to 3 millimeter in diameter, and the length not more than 5 to 6 millimeter. So, that is, and the coil, the heater coil has to be very small, my miniature heater coil. Okay. So, this is the basic design of a gas sensor. So, it is a self heated sensor. When we are talking about sensor, one or two parameters are very important, how to express or how to know what is the effectiveness of such a sensor. So, to measure the effectiveness, we have 2 or 3 parameters we are normally used in sensor technology or sensor area. First of all, the sensitivity. Well, there are 1 or 2 different ways of measuring the sensitivity or make a quantitative measurement. This is the resistance initially, that is the stable resistance in air. So, that is your reference. So, air is the resistance, and normally this resistance is higher than in presence of gas. If you are talking about primarily reducing gases, and some of the reducing gases are combustible gases also. So, from that point of view, resistance in presence of the gas will be lower than that of the air resistance, okay. And then you divide it by air resistance. So, it becomes actually less than 1, okay. It should be this will be lower and this will be higher. So, it is normally less than 1, it may be greater also. Or sometimes it is also, in some literature you will also find that it is just the ratio of resistance in air to resistance in gas. So, that also becomes a higher than 1, ratio becomes higher than 1 in this case. Okay. So, this is normally plotted either against time or against gas concentration to show the sensitivity. So, that is the sensitivity of a sensor. And then selectivity. Now, selectivity, of course, there is no quantitative parameter for that, but basically whether we are able to accurately measure the specific gas concentration from a mixture of gases. Okay. There may be different gases, hydrogen, maybe carbon monoxide, maybe some other hydrocarbons and so on. So, whether we are able to distinguish between these different kind of gases, that is what we call the selectivity. Okay. And in general, as we have seen from the discussion in this lecture itself, that the selectivity of this kind of solid state sensor or oxide based sensor is not very high. So, whether it is a carbon monoxide or a hydrogen, both of them are basically reducing, and they will react more or less in a similar manner with the adsorbed oxygen, and therefore, enhance the electronic conductivity more or less in the same manner. One may be little higher than the other, but accurate sensitivity or the measurement of hydrogen separately and carbon monoxide separately becomes difficult. So, this is one of the disadvantages of this kind of sensor. Selectivity is relatively poor. However, if somebody knows that there is no presence of, there is only one kind of reducing gases or one kind of oxidizing gases, then it becomes easier to understand whether the gas concentration is increasing or decreasing, at what rate is it increasing, and so on. And sometimes through a calibration process, one can also find out the accurate measurement of the concentration of the gas of our interest. Now, in this context, I will come to that in a minute. Before that, there is another parameter, I think better I introduce that. It is the response time. Okay. How fast it can respond to a change in concentration. Okay. So, that is another important parameter, and the response time has been basically defined the time needed for a resistance change of at least 90% of the resistance at air for a fixed concentration of gas. So, you introduce certain concentration of gas and see how much time it takes to change to that or to respond to that particular change. If we are changing the concentration from maybe from 100 ppm to 200 ppm, then 300 ppm, that change may be instantaneous, but the sensor may not respond immediately. It may take some time, there may be a time lag to respond to the changes what being introduced, and therefore, response time is also very important. And in the process of response time or in the context of response time, there are two aspects. One is the response to the changes. It may be enhanced concentration or reduction in concentration. Okay. So, you can withdraw the gas and see at what rate it is recovering. So, one is the response time, another is also the recovery time. Mostly the response time is faster, that means the enhancement or the reduction in resistance is faster, whereas the recovery is slow, because they are kinetically not a very fast process. So, it is basically there is a need of mass transport and adsorption desorption process. So, all these processes are relatively sluggish processes, and therefore, although the response time is fast, but the recovery time is relatively slow. Now, it can vary depending on the particular oxide, depending on the way the samples have been prepared or the surface structure, also this area of the surface, all these things are important, which changes the different parameters like response time, sensitivity, selectivity and so on. So, the response time may vary from fraction of a minute to more than a minute. It is not in the range of milliseconds or microseconds, it is not like that. It is relatively slow process, but certainly within a minute one can respond very stably. So, the equilibrium can come within a minute at least. Sometimes of course, recovery can take a little longer, maybe 1 to 5 minutes or so. So, before that one cannot expect some accurate changes in the conductivity or the response behavior. So, these are some of the parameters one has to remember while using a gas sensor of this nature. Coming back to the last point which we mentioned here, the electronic nose. Okay. Basically, our nose senses various kind of aromatic compounds, some smells and so on. These smells are nothing but the presence of certain gases. Okay. Some gases actually produces some smell specific to the particular situation or fragrance and so on. Sometimes smells are also there, bad smells are also there. So, even some rotten things produces some bad smells. So, from that is basically generating certain very fine very small quantities of gases, different kind of gases, that is the smell. Okay. So, by measuring electronically, by measuring the concentration of these gases or a mixture of gases, one can replace the human nose by an electronic instrument, and this is nothing but what we call an electronic nose. So, there are tremendous amount of development going on. It is a very difficult task, no doubt, because when you sense a particular smell, it is not a specific gas or one gas. It is a mixture of various large number of gases of similar nature, maybe similar nature, and distinguishing those gases becomes quite difficult. And therefore, if you want to really replace a human nose by a electronic instrument, it is not a very easy task. Now, most of the cases what we do, we do not use a single sensor, but a array of sensors, a large number of sensors with certain characteristics, with certain different characteristics. Okay. So, they have maybe sensitivity, one may be sensitive to gas A, another may be more sensitive to gas B, another may be sensitive, little more sensitive to gas C. Complete distinction is difficult, but their relative sensitivities can be changed by manipulating some of the preparation techniques or the design techniques. So, this can be there will be a array of such sensors, and for making an array of sensors it is better to have a miniaturized sensors, right, as small as possible, and from that point of view the sensors which are used in arrays are called MEMS based sensor. They are actually miniaturized sensors, micro electromechanical sensors, and they are basically fabricated by the so called VLSI technology, large scale integration or chemical vapor deposition kind of techniques, not thick film technique, but mostly thin film technology. So, the fabrication techniques are little costlier, but one can get a miniature sensors of the order of let us say few sometimes less than a micron, less than a millimeter, or tens of microns. Okay. So, such sensors can be placed by a thin film technology on a substrates, and each one of them, the way we have our microelectronics technology, each pixels in a display can be electronically connected. So, here also of course, they are not as small as pixels of a display, but it is slightly larger, but they individually can be monitored and measured. Okay. So, when a gas concentration comes in contact with all these array of sensors, each individually one can monitor what is their response, what is the electrical signal from them, and then each one of them will have some kind of a differentiation. For example, one can different sensors can be placed at different temperatures, and by that process one can differentiate their response times, their response to a particular gas, and so on and so forth, and their catalytic activity can also be modified. Okay. Instead of palladium you use maybe silver palladium, maybe gold palladium, and so on, so that different sensors senses different gas with relative less or more importance, and by that process you get large number of signals, electrical signals, which can be then processed through a software, and you can get a signature analysis of all these signals, electrical signals coming from different maybe 100 different sensors, and then try to find out what is the nature of that particular gas mixture. In fact, there are many different things people are using it. These sensors may be the fish quality, whether it is good fresh fish or rotten fish, that can be sensed. In fact, there has been lot of attempts, some of the instruments are already available in the market. Fruit sensor, fruit freshness sensors can also be there, and people, in fact, there are some groups in this country who are working on these kind of sensors, different kind of array of sensors also, and even the quality of tea, because quality of tea depends on the kind of flavor it generates, and that flavor again comes from a large number of aromatic compounds, several tens or hundreds of them are available. It is very difficult to identify them, but as a collective measure you can have a signature of different flavors. So, by that one can, by using this kind of a sensor, a large number of sensors together, one can replace human nose and get an electronic nose. So, that is one thing being tried even in this country. Several research groups are working in that area. That we have discussed. Response time, this is the last one for the time being. That is this kind of typical sensitivity of sensors. Well, these are schematics only. These are schematics only, which what has been plotted here as a time sensitivity, different concentrations of the same gas. Of course, this is not a mixture of gas, the same gas has been introduced at different times, and see how the response changes, or the sensitivity changes, or the signal changes, the strength of the signal changes. Okay. So, this is C1 concentration, C2 concentration and C3 concentration of the same gas, maybe carbon monoxide, maybe some alcohol. C1 is less than C2 and less than C3. So, this concentration is less. So, the overall signal is intensity is less. Then in fact, the resistance are changing, there is less resistance, this is higher resistance, this is lower resistance. So, lower resistance means larger current, and still lower resistance, larger current, basically it is measuring the current. So, it is proportional to current, and this is the your kind of response time. Okay. From this is the time scale. So, at this time it can be a 0 time here. So, how much time it takes to goes to the saturation. So, that from this point to this point is your response time, and you can see the recovery when it is withdrawn, this particular gas concentration withdrawn, it is coming back to 0, but it is a slower space. Okay. So, this recovery time is slightly larger. Same thing happens once a different concentration gas is introduced, once again it reaches a saturation and then it continues. This is gas is withdrawn. Okay. It is coming down, not because of anything else, but because the gas is withdrawn here. Once again a different concentration is introduced and the signal goes up, and once again the C3 concentration withdrawn, and it takes some time before it comes back to its original position. So, this is the typical response behavior of sensors to the. So, we have sensitivity as well as response time, and different sensors responds differently at different temperatures also. So, temperature is another parameter by which one can change the response time as well as the sensitivity. Now, one of the reason or one of the characteristics one has to measure for any sensor, it is the linearity as a function of concentration in particular, since we are interested in concentration. So, as a function of concentration, are we getting a linear change? That is a very important issue. Well, in some region we do get linearity, but it is not always linear throughout the concentration range. So, some kind of calibration curve are always necessary, and compare if we are interested in a a specific concentration or a not a relative term, but absolute concentration. If we are interested in absolute concentration, we need a calibration curve with respect to the concentration at different temperatures, and try to find out what is its response and what is its sensitivity. So, with this we complete this particular lecture. We will continue this discussion on ceramic gas sensors maybe in the next class. So, for the time being, thank you very much.